parameter using SMOT's optical thickness.
Thank you all for being here. Like you said, I'm going to talk about this stuff called B parameters, SMOS, optical thickness, which is kind of different than some of the other things that people talk about. But it actually is a little bit of similarity with the last talk. But I'll go over some of this jargon here. Since this isn't really a SMOS session or a soil moisture session, just so everyone's on the same page. And I'd like to acknowledge my co-author and advisor, Brian Normal. So first, what is SMOS? It stands for Soil Moisture and Ocean Salinity. It's the satellite mission that was launched by ESA a couple years ago. It's a passive L-band satellite, and it has a pretty large resolution, 40 kilometers. But that large resolution actually works really well for what we're trying to do because, as I'll explain a little bit more about it, it's about the same size as an Iowa county, and what a county is, I can help explain that too in a little bit. One of the really neat things about SMOS, though, is that it measures at multiple incidence angles. And because of that, it's not only able to retrieve soil moisture, but also this parameter called optical thickness simultaneously. And so what is optical thickness? And it's this parameter tau in the tau omega model that's sort of the emission model, the microwave emission model that we use. And so just to point out where that is here, I'm not sure how well it's easy to see with lasers, so I'm going to try to use the mouse here. So it shows up 4 times in this equation, all of these exponentials, and so obviously it's doing some attenuation, but along with that, if you consider these 3 different sort of contributions in this equation, not only is it attenuating, but it's also acting as to the radiation that's being emitted by the canopy itself. And the reason why there's radiation being emitted by the canopy itself is because not only does the soil have water, but the canopy has water. And the way that you can relate tau, and I'm going to use tau in place of optical thickness probably for the rest of the talk. The way that can be related is just through this parameter B. So tau is B times the vegetation water content. The vegetation water content is kind of a density, so the kilograms of water in vegetation per like meter squared of ground. So I just want to, since I'm going to kind of jump off some previous work that I presented. This is from last year's IGARSS talk, and so we looked at this tau data that SMOS produces. Again, this is just an example from a single county, and I'll get to what a county is exactly. But one issue that we saw is that so each of these little dots here is a single measurement of tau, and there's a lot of noise in the data. But it turns out that if you do a moving average or do something else to smooth the data, you do still end up seeing this signal over the growing season. So this would be, again, this is an area like the previous talk where there's a lot of corn and soybean growing. And so you see the maturing and senescence of the crops there. There's some other interesting things going on though. The tau is changing outside of the growing season, even though there's not a lot of other vegetation in this area. And we found that was probably due to changes in surface roughness that weren't being accounted for in other ways by the SMOS retrieval algorithms. And then we used this tau data we wanted to try to find a way to validate this tau data, and the best thing that we could really come up with was using crop yields for each county in Iowa, and then compare that to this maximum change that you see in optical thickness. So this would be like the minimum at the beginning of the season, and the maximum as the crops are maturing. And we found a pretty good relationship there, pretty linear, and it pretty much fits right through the origin. So that's nice and all. But we wanted to improve upon that a little bit and extend this analysis a little bit further. So one thing that was suggested that SMOS being noisy may just be because we were using an old version of the data. So we got all the reprocessed data. The latest version it's 5 or greater now, the level 2 processed data. But it's still really noisy. So this is basically the same thing as we saw before, 2010, and then even throughout the last couple of years, it's still looking pretty noisy. Another thing is that the way that we calculated tau for a county is we had some sort of bleeding going on in the other county, so we averaged everything out. So this time around, we just looked for we computed the centroid of each county. So this is a map of the state of Iowa. Each of these boxes is an Iowa county, and it's about the same size as a SMOTS pixel. So it's kind of 40 kilometers by 40 kilometers for the most part. Obviously, there are different sizes throughout, but on average, it's about 40 kilometers by 40 kilometers. So we computed the centroid, and then found which SMOS pixel was closest located to the center, except for some rare locations where that meant that we were missing a lot of data, and then we just picked the next closest. And then as I showed before, we did this moving average for smoothing. That wasn't very satisfying, so I'm working with a statistics student actually right now on some better ways of smoothing the data, and so we're using that analysis, using some functional data analysis techniques. And then, so this is just showing the couple of years that now, and you can see now, yeah, so before it was only 2010, now we've extended this analysis through 2012. But so what? I mean, I'm not just going to, if I'm up here just reinventing the wheel again, I mean, why am I even up here? So doing all these improvements, we actually kind of played around with some other variables, and we're looking at some things, and actually decided that, hey, we actually might be able to calculate that B parameter that I mentioned before by looking at these relationships between tau and crop yields. And if we make some assumptions and look at some different elemental relationships, then we may actually be able to calculate the effective value of B for each Iowa county. And sort of our test of this is that the values of the estimates of B that we get from doing this should be somewhere in between literature values found for B from like tower experiments for maize and soybean, corn and soybean. So what are these assumptions and relationships? Well, the first one I've already kind of mentioned, but I just want to make sure that this is just a little slight difference here. Again, I'm talking about the change in tau, so the maximum change over the growing season. And then we're saying that should be related completely to just the vegetation, the water content in the vegetation. And so that should be, basically the peak in tau should match up with the maximum amount of water in the vegetation, so I call it VWC max. Now that maximum VWC should in some way be related to the maximum dry matter in the crop. And so I'm going to introduce this parameter called theta GV max. It's basically something we invented, so I'm going to try to go a little bit more into about what that is. And then we have to figure out a way to actually relate these crop yields to the maximum dry matter. That's through this parameter called harvest index. Here I have it as HI. And then as I showed before with that nice linear fit, you can relate delta tau to crop yields. And so if you put all this together and do some algebra, you can actually solve for B and come up with this. So B is going to be the harvest index divided by the slope of that line times this thing that I'm calling theta GV max. So what the heck is this theta GV max thing? So I like to think of it as, coming from sort of a little bit more of an agricultural background, I think of it as like the gravimetric vegetation water content. But the easier way to think about it is just the ratio of the maximum water mass over the growing season to the maximum dry mass measured over the growing season. And this isn't defined at a single point in time. In fact, it's two different points in time, because as the previous speaker showed some data from me, here's some more, looking at some corn. They went out and measured the fresh mass of plants and the dry mass of plants. And what happens is that the time of peak water content is actually different from the time of peak dry mass. So those are two different times, and so what we do when we calculate theta GV is take the peak water and the peak dry matter, and then just basically find the ratio there. And yeah, this is off. That should be per hectare, not per meter squared. That's humongous. So when we do that, we find that for corn, the theta GV max is around 2.6, and soybean it's around 2.7. But we only had a few data sets to calculate this from so far, so we're not completely sure about the stability, so I've got some confidence intervals here. And we definitely need more data on soybean. Nevertheless, we charge ahead, and talking about harvest index, so there may be some people here that are familiar with what harvest index is, but it's a pretty common parameter used in crop modeling. It's also been kind of used as a tool for seeing how well crop seed technology has improved. Because the idea is you want to have a higher harvest index, because then you're putting more carbon into the grain, into the yield, than into leaves and stems. And so yeah, harvest index is just the ratio of the yield to the total above ground dry mass. And I don't have any other pictures for this one. But I've just taken values from the Oak Ridge's carbon dioxide group there that they're trying to do studies on carbon storage. You'll find a lot of different values because, as I talked about with seed technologies changing, carbon yields have gone up over the last few years. You can argue that maize should be more around 0.55 now, and soybean, you can see lots of values. You'll see lots of values in literature. But I think it's more of a function of time than just true variability. And so then again, I've gone through, so I had that one slope for 2010, but we've made some changes. So we've gone through and updated those slopes for the last 3 years. And so one thing that we noticed after making some tweaks is that the data does not fit, the linear regression doesn't fit quite as nicely through the origin. So I'm calculating 2 slopes for each of these lines, one with the y-intercept, of course. And I'll consider both of those when doing the computation of B. So in 2010, this is basically the same thing as I showed earlier in the presentation, but again with those tweaks involved. 2011, the slope was a little bit less steep, and in 2012 it was the least steep in terms of having basically higher delta tau values for the same sort of yields. So we take all those slope values and plug them into our equation, and now we can finally get estimated values of this B parameter. And so I don't want to show like every single year, every single county, so here's some averages for the last couple of years. So when we do that, we find that, let me back up. So B0 is going to be the B calculated from the fit through the origin slope values. And then B1 would just be the slope that would just be sort of the regular linear regression that has a y-intercept. And so you see that the B values for the line that's fit through the origin are quite a bit higher. And that's true if you look over at counties also. So here's just a couple. These are the top 3 and the lowest 3 counties in terms of their B values that we estimated, averaged over the 3-year period. And one thing that you see is that the higher the corn to soybean ratio, the higher your B value is going to be. And that makes sense because in literature, and I'm going to show you some specific values here in a second. In literature, the B values for corn are higher than they are for soybean. So it makes sense. At least these numbers make sense conceptually. But the real question is do they match this test that I've come up with? That the B values that we're estimating here should lie between literature values of corn and soybean. Well, here are some literature values, and even if we sort of take a really aggressive approach and assume that this low-end estimate of the B value for maize is the correct one, you still sort of get the idea that these estimates that we're getting from this method are a little bit low. You can see that in 2010 we didn't even get up to the B value for soybean. In 2011 it was close. 2012 looks like more something like we would expect because more corn is grown in Iowa than soybean. At this point, I mean, can we estimate this B parameter from SMOS tau and crop yields? Well, probably not yet. We're a little low. There's some things that we still want to tweak with this method. But at least it shows some promise. We're in the ballpark here, but it's definitely not something that you would want to use and say. For example, another soil moisture satellite is going to be launched soon by NASA. It's called SMAP, and they need outside values of tau, which they're going to try to get from getting outside values of vegetation water content. And so they need B values to be able to convert that from BWC to tau. But it's really hard to get any estimate of what B is supposed to be at this county level scale, these really large scales. And SNAP is going to be working at about 36 kilometers, so it's still a really large area, and it's hard to get measurements, power-based measurements. You can get close with airplane-based, but it's still really difficult to figure out what B is supposed to be at that scale. And just some extra notes. We still need the SMOS tile is still noisy in the latest versions of the data. Part of what I'm doing with the statistics student that I was talking about before, and fitting these curves, is also trying to figure out what the characteristics of the noise are. So maybe we can actually start getting to a point where we can start figuring out what's actually causing the noise. As I said before, we need more theta GV max data, especially for soybeans. So if anybody has good long-term like fresh mass and dry mass of soybeans data, then that would be awesome. And then we also want to make sure that we characterize the stability and air in any of these other parameters that I mentioned, so like harvest index. So with that, thank you for your time.
Time for questions? Let me ask one question. Your way of estimating this important problem, the harvest index, is very unique, and of course it's still in the explorative stage, as I can see. But to understand the physical basis for that correlation, why you correlate the tau to harvest index, not the total biomass? Is it because the yields, the grain, have different water content, a lot more different water content than the total biomass itself?
So I want to make sure I understand your question. So why are we trying to basically, Adrian's asking why we can try to compare dry matter to tau, or?
Yeah, but the harvest index,
Right.
Why harvest index physically can be related to your value, tau value?
So that goes back into so if I bring that back up here, that goes into the whole chain of relationships. So yields, so one way that you can estimate yields is if you have, like, for example, if you think about having a crop model where you estimate the total dry matter in the crop as it's growing in your model, then at the end of the season, if you just multiply that by a harvest index, then you get what your yield is supposed to be. And the only really big measurements that we have on the county scale of vegetation are yield estimates. And so what I'm using with that harvest index is to go from yield to the total dry matter in the plant. And the total dry matter, not just in the plant, but sort of the average total dry matter over the whole county for any like year. Does that answer the question?
Yeah, I understand. In that case, you need total biomass.
Right.
It's going to get the yield. It's not in that relation to the yield index.
Well, that's what the harvest index is supposed to give you. It's supposed to go from yield to the total biomass.